Welcome you all to Principles of Organic Synthesis. So far we have studied aliphatic carbon nitrogen bond formation, organometallic reagents, aromatic electrophilic substitution, aromatic nucleophilic substitution, and the preparation and the reactions of aromatic diazonium salts. Today we will start the new topic, molecular rearrangements. If you look at all the lectures so far that we had, where if you remember the basic skeleton was remain intact. Today whatever we are going to study, where we can find there will be rearrangement in the basic skeleton. The rearrangement can be intramolecular or intermolecular. The rearrangement can take place within the molecule, or the rearrangement can take place between two molecules, which is known as intermolecular rearrangement. The rearrangement can occur to electron deficient as well as electron rich systems. Today we will see the rearrangement to electron deficient carbon. Here an example shown. This is Wagner-Meerwein rearrangement. If you look at this example, albapinine, which undergoes when you react with hydrochloric acid, it gives isoamyl chloride, and this is some of the points you have to try to remember in the case of Wagner-Meerwein rearrangement. And if you take alcohol, and we will see next, when you react with acidic medium, already you know that dehydration can take place. You will be able to form a carbocation which can lead to rearrangement. The driving force for the rearrangement is the greater stability of the carbocation. If you form, for example, primary carbocation, it can rearrange it to secondary or tertiary carbocation because they are more stable comparing to primary carbocation. The cations can be made more stable if they become less strained. This we will see some examples. Now let us look at this reaction. The reaction of albapinine with HCl, it gives isoamyl chloride. As all of you know very well, when you react the substrate with acid, it can undergo addition reaction, then you will be able to form a tertiary carbocation. It is actually a nucleophile, electrophile. It can undergo addition reaction, already you know very well, and you will be able to form a tertiary carbocation. Now the tertiary carbocation can react with Cl minus. You will be able to form this compound, but doesn't happen here. Once you form the tertiary carbocation, what happens? Now you have the 4-membered ring, which due to strain, now this carbon now migrates here. So you get secondary carbocation. As soon as you form, this doesn't happen here. Instead of that, you form this secondary carbocation. So here, if you look at here, although this tertiary carbocation more stable, it goes to the secondary carbocation. Once you form this one, now this reacts with Cl minus, and you get the product. So in this case, what happens? As soon as you form, it converts into less stable secondary carbocation, because this is to relieve the strain that you have from 4-membered ring. When you convert 4-member to 5-membered ring, it gets relief from the strain, because this is a more strained one, 4-membered ring, and it can migrate to here this carbon. So now you generate a 5-membered ring which is less strained comparing to 4-membered ring, and once you form this one, now this can react with the Cl minus. You will be able to get this compound. So this is an example. Now you can look at here, and as soon as you form the carbocation which rearranges to give you an intermediate, more stable carbocation. That carbocation now, particularly in this case, the ring stain plays a very important role. You form this secondary carbocation that reacts to give the product. As all of you know very well, in this reaction there are two steps are involved. First, you form the carbocation, then the addition reaction takes place. So this is the rate determining step. The first, the formation of addition reaction is the rate determining. Once you form this one, then it can rearranges, and then you have the another carbocation which undergoes reaction. You will get the addition product. Here another example shown, the reaction of alkyl halide with Lewis acid, silver plus, in the presence of which can undergo reaction to give a carbocation. That carbocation undergoes reaction, you get this. So the intermediate, this one. So once you have this alkyl halide, when you react with the Lewis acid, and then it can convert into primary carbocation, silver bromide. Once you form this one, now, so this is the rate determining step. Once you form this one, now this can migrate and to give a secondary carbocation. Now it can migrate, give you a tertiary carbocation. You look at here. Now you have the primary carbocation. When you do the migration, you get the tertiary carbocation, which is more stable comparing to the primary carbocation. So this is the driving force in this reaction. As soon as you form the primary carbocation, is converted into tertiary carbocation, which is more stable. Once you form this one, now you can lose a proton, you will be able to have alkene. Alternatively, if you have nucleophile, in this case you have the ethanol, so which can react, you will be able to form ether as the product. So once you form the primary carbocation, it rearranges, you get the neopentyl cation, tertiary one. Once this tertiary one is formed, which can undergo reaction with nucleophile, depends upon the reaction conditions. Here you have the ethanol, which can undergo reaction, you will be able to get. And as I mentioned, the first one is the slow step, and second one is faster, and during the reaction takes place. So the rearrangement reaction is sometimes very useful. That depends upon the nature of the substrates as well as reaction conditions. They are very important to carry out this transformation. So we have seen one example for alkyl halide. Similar way you can try to do. For example, you can also use, for example, this alcohol. So this alcohols also, when you react with acid, you will be able to form similar way primary carbocation, which can rearranges to get this. And you can also use alkene. For example, this also, when you add acid, as we have seen, can undergo addition reaction, and you will be able to form. This can again migrate, so we will be able to have here primary carbocation to tertiary. After migration, you will get this. And similarly, in this case too, once this migrate, now we have the secondary carbocation, it can now, the methyl group with the bond pair can migrate here. So you will be able to form tertiary carbocation. You will have this one. Once you form this one, this can now undergo reaction, depends upon the reaction conditions. If you have the nucleophile, it can undergo addition reaction. Otherwise, it can lose proton, you will be able to get alkene. You can also, in place of this one, you can also use amine. For example, you have this primary amine. When you react with the nitrous acid, already we have seen, so you can make diazonium salt. Once you form this one, you will be able to form primary carbocation, which can lead to rearrangement, as we have seen. So that's only I mentioned, just nature of the substrate. You can use alkyl halide or alcohol, depends upon the reaction conditions and the nature of the substrates. They can lead to rearrangement to give a more stable carbocation, or we have seen one example where the stability of the system is very important. If you have 4-membered ring, it can try to convert into 5-membered ring to relieve the strain. In this way you will get the rearrangement carbocation, which can further undergo reaction to give the addition or elimination product. Here the reaction of isobonial shown, which can in the presence of acid can convert into camphene. So far the first example also bicyclic system, then we have seen the linear molecule. Now let us look at the rearrangement of this reaction. As just we have seen, so when you react with acid, so which can lose water molecule, you form a secondary carbocation, which can undergo rearrangement as shown here. You have the sigma bond, which can, this bond can migrate with its bond pair to give So now let us look at here, when you add a proton and you get this protonated species which can lose water molecule to give a secondary carbocation which rearranges to more stable tertiary carbocation. This is a driving force for the rearrangement of this secondary to tertiary carbocation, because this is more stable, it can rearranges. Once if we rearrange, now again as I mentioned, depends upon the reaction conditions. If you have the nucleophile, it can undergo addition reaction or it can lose so you can lose the proton, then you will be able to form which is so this is equivalent to camphene. So in this reaction, protonation followed by dehydration gives this protonation followed by loss of water to generate the secondary carbocation, which can rearrange to more stable tertiary carbocation. Once we form this one, which can convert into this alkene by losing protons. So this how this reaction takes place. The driving force in this reaction is the formation of tertiary carbocation from the secondary carbocation. Once you form this one, then it can convert into this alkene as the product. Next example, the reaction of this alcohol with this acid can give this alkene as the product. And in this reaction, as just we have seen, the protonation can give this molecule which can lose water. You will be able to form carbocation, the secondary carbocation. Once we form this one, now So two possibilities there. It can convert into alkene by losing this proton. This doesn't happen. This is because the double bond is present and the bridge head is very strained, so it doesn't cannot form the double bond here. Therefore, and the other possibility is there. Now this can migrate here. So this methyl group can migrate to this carbocation with this bond pair. So to give you have the carbocation which can now lose proton. You get the. So as you can see here, the reaction depends on the nature of the substrate. So in this case, the methyl group migrates with this bond pair to this position, then removal of proton give this alkene as the product, because this other alkene doesn't form. This is because this due to strain, and this carbocation undergoes rearrangement, and then you get this tertiary carbocation. You have secondary carbocation undergoes rearrangement to give the tertiary carbocation. Once if you give this form this one, which can convert into the alkene as the product. Here the rearrangement of a polycyclic system is shown here. If you look at this example, and when you react with acid, as just we have seen, and you can lose water molecule, then you will be able to form a carbocation. Once you form the carbocation, so you have to remember in this always the rearrangement that whatever the incoming group comes opposite to the leaving group, like SN to reaction with inverted configuration. Therefore, when you react this one and then you have the carbocation, in this case the hydrogen migrates here instead of methyl group. This is anti to that leaving group, therefore hydrogen migrates here. Now we have a carbocation. Now then this methyl group migrate. So here methyl group migrates, then you get another carbocation here. So you have the carbocation. This carbocation, now this methyl group migrates here, and you have another carbocation. Then this group comes here and goes on like this until you have the carbocation here. If I write, it will take time. And what happens here? You form the carbocation. Once you form the carbocation, the hydrogen migrates. Once migrates, you have another carbocation. Then this methyl group comes here, and look at here. And if it comes the top side, anyway, here there is no difference when you come this one. Now let us look at here. Now the hydrogen comes the same side. The leaving group is opposite side, the top beta side, top side, this methyl group migrates, and the bottom side, the hydrogen comes here. Therefore, it comes this one like alpha. And now once this comes, the top side, this methyl group migrates. The bottom side, this hydrogen comes here. The top side, this goes here, and this bottom side, and you will have the carbocation. Once you have the carbocation, now it can lose proton, then you will be able to get these compounds. See what happens here. Here 7 successive 1-2 shift takes place. 1, 2, 3, 4, 5, 6, 7. 7 successive shift takes place, then you will be able to get this alkene as the product. Now let us look at Here, as you can see here, 7 successive 1,2 shift takes place, and you will be able to form this alkene as the product. The next example, let us look at this one. As just we have seen in this case, and when you react with this Lewis acid and acetic anhydride CY, this elimination of this can produce a carbocation. Once you form the carbocation, this methyl group can migrate with this bond pair to this carbon, the top side. So you will have this one, make a new carbon bond, and you have the carbocation. Now the bottom side, the hydrogen with its bond pair can come here, and in this way the migration takes place. In this 5, 1,2 shift takes place. You can see here 1, 2, 3, 4 and 5. So you can see here this in this way you can try to convert. You can see here this is the reaction stereospecific. Always the migration takes place from the opposite side to the leaving group. In this way the reaction can be stereospecifically can be carried out. Here another example shown. In this case, whatever so far we have seen, where in one case we had the hydrox group which we treat with acid, you can convert into carbocation by losing water molecule, which undergoes rearrangement. The second example we have seen the removal of acetate group using the Lewis acid, which can form the carbocation that can lead to the rearrangement to give the alkene as a product. In this case, you can see here you have the double bond as well as OH group. In this case, the OH group is intact, and the double bond, when you react with this acid, it can undergo protonation. Once you form the protonation here, you form carbocation in this place. Now, once you make the carbocation, this methyl group migrates here with its bond pair bottom side. Then you have another carbocation. Now, this methyl group migrates 1,2 shift from here to there, the top side, and you have the carbocation. The bottom side, now the hydrogen with its bond pair migrates, and you have the carbocation here. The top side, the methyl group migrates with its bond pair, and similarly it goes on. Then you will be able to get this compound. You can see here the reactions stereospecific once again. So the rearrangement can be carried out, and you will have now carbocation. The tertiary carbocation again now reacts. This methyl group undergoes migration. In this case, this methyl group can undergo, because this is the top side can undergo here, and then 1,2 migration. So with bond pair you will have the carbocation. Once you have this one, now this can lose proton, then you can get the alkene as the product. So far we have seen the migration of mostly alkyl group. Now let us look at the migration of aryl system. Now let us look at this alkyl halide, where you have the phenyl substituent. When you react with Lewis acid, as just we have seen, for example, when you react with silver plus, and you can form a carbocation. In this case, you form a phenonium ion. This, once you form this, and this provides by due to the neighboring group participation of this aryl ring, you will form this intermediate. Once you form this one, now this can convert into this tertiary carbocation. You have the primary carbocation. You are through the enzymatic assistance you form of the phenyl group, you form this intermediate. Once you form this one, which can convert into this tertiary carbocation, which can now lose proton, then you will be able to get this styrene derivative. If you compare the reactivity of the methyl group or alkyl group with this phenyl one, this under same reaction conditions, the phenyl ring shows greater reactivity comparing to the methyl group. This is because of this system enzymatic assistance, and the reaction is facilitated several times faster. In addition to that, if you have here electron donating group, for example, the aromatic ring, for example, if you have the methoxy group, or methyl or electron withdrawing group. So, the reaction that contains electron donating group shows greater reactivity comparing to that having the electron withdrawing group. This because of the electron nature of this aromatic system. If the electron rich, it can facilitate this neighboring group participation, then the reaction can be facilitated. Therefore, whenever you have the electron withdrawing group, donating group, the aromatic ring, and such system shows greater reactivity comparing to that having electron withdrawing group. For example, if you compare this one with benzene, and this has electron donating group shows greater reactivity comparing to benzene. If you have electron withdrawing group, again this will show greater reactivity comparing to that having electron withdrawing group. We compare with alkyl group, this aromatic system shows greater reactivity comparing to alkyl group. This is because of the enantiomer assistance of the aryl system. Here the reaction of alkyl amine is shown. As we have seen earlier, this in the presence of nitrous acid, it can form the diazonium salt. Once if you form the diazonium salt, now it can convert into the carbocation, and once you form the carbocation in this case, and this is a primary carbocation, and now if the hydrogen shifts with this bond pair, then you will be able to form a secondary carbocation. So, this is the driving force in this reaction. You convert from the primary to secondary carbocation. Once you form this one, now if you have the nucleophile, in this case you have the water which can undergo addition reaction, you get the isopropanol as the product. It can also lose proton, then you can form this alkene propene as the product. So, already you know that how you can form the diazonium salt. We have seen earlier. We have once you form this one, now this can, when you undergo protonation, so this can lose water molecule, you will be able to form the salt, diazonium salt. Once you form this one, and it can be easily converted into the carbocation by losing nitrogen. And once you form this one, which can, in this case, the hydrogen shift takes place, the hydrogen with its bond pair can move to this carbocation, you will be able to form the secondary carbocation. Once form this one, which can be further converted into neutral molecule. In this case, if you lose proton, you get the alkene. On the other hand, if you react with the water molecule, and you will be able to get alcohol as the product. Here the reaction of this alcohol are shown, tricyclic system. You have here 6-membered and 4-membered and 5-membered ring, and there when you react this molecule with 40% sulfuric acid, the formation of this product observed. In this case, ring expansion of this 4-membered ring happened. As we have seen earlier, when you react with acid, you end up with this tertiary carbocation. Once you form this one, as we have seen earlier, you have the 4-member ring. Now this bond can undergo migration to give So we will have this secondary carbocation as just we have seen earlier, and although you have the tertiary carbocation and it is converted into secondary carbocation, this is to relieve the strain of the 4-membered ring. So this undergoes migration here, and you will be able to form a 5-membered ring and 6-membered ring once you form the secondary carbocation. Now this can react with water and you will be able to get this product. So in this case, as we have seen in the case of albapinin, here also the relief of the strain of 4-membered ring dominates comparing to the stability of the carbocation, where the tertiary carbocation is converted into secondary carbocation through this rearrangement. Once you form this one, this can further react with water molecule to give this alcohol as the product. So far we have seen some examples for the Wagner-Meerwein rearrangement. As you can see here, the reaction is stereospecific, and we have seen examples for the migration of hydrogen methyl group as well as aromatic system. They migrate with their bond pair to the electron deficient carbocation. In some cases we have seen the stability of the carbocation plays very important role. If you form primary carbocation, it is converted into tertiary carbocation to then the reaction takes place. In some cases we have seen the ring strain plays very important role. If there is a 4-membered ring and it can rearrange to 5-membered ring so that it can relieve the strain. This some of the examples we have seen where the carbocation is converted from tertiary to secondary, where the ring strain plays very important role comparing to the stability of the carbocation. Now let us look at the Pinacol rearrangement. If you have Pinacol, when you react with the acid, and as we have seen, it's similar to the Wagner-Meerwein rearrangement, and you can do the protonation and form the carbocation. Once you form the then it can undergo migration. You can get this compound, this one. So Pinacol can be easily made. All of you know very well. If you have the ketone, so if you give electron, so it can convert into. So you can dimerize and you will make the For example, when you react with so you will be able to get the corresponding diol as the product. So now when you react this Pinacol with sulfuric acid, you get this ketone. When you look at the reaction pathway, when you add acid, protonation of hydroxy group, once you form this one, now once you form this one, this can lose water molecule. You form a carbocation, as just we have seen. Now this can migrate with this bond pair, so you will be able to form this intermediate, which can lose a proton to give the ketone as the product. So if you have the diol, when you react with acid, it can be converted into ketone. This feature of this reaction is similar to that of Wagner-Meerwein rearrangement. Here also the carbon migrates to electron deficient system. You form a carbocation which undergoes reaction. Here an example shown here. This reaction also stereospecific. Now let us look at this dimethyl cyclohexane diol. So in this case, if you look at here, you have this, if you see the relationship between this OH group and this one, both are axial. This means trans. When you do react with acid, in this case, the protonation, for example, if it takes place here, you will lose the water molecule. You form the carbocation. Now this can migrate here and you will be able to form this ketone as the product. On the other hand, now let us look at this one. In this case, if you see the relation between this one, this is equatorial, this axial, and similarly this axial, equatorial, the relationship is cis. Equatorial, axial, equatorial, the relation between this OH group and methyl group is cis. So when you react with acid, in this case, for example, if you form the carbocation, so this now, since now this can now undergo reaction, this bond can migrate here, then you will be able to form in this case you will be able to form a this 5-membered cyclic compound which can lose proton, so you will be able to form this ketone as the product. So this just we have seen the case of Wagner-Meerwein rearrangement. Here although stereochemistry is very, the reaction is stereospecific. If we have the trans relationship between these leaving and migrating group, then the reaction takes place. This is what happens here. And similarly, what also happens here, since the relation between this and this are trans, then the migration takes place. Between these two are cis, so therefore in the place of this, in this compound, and this bond migrates instead of this methyl group, you get the cyclopentane derivatives as the product. Now let us look at the reaction of this diol, and here as just we have seen protonation of this so one of the OH group can give this carbocation. This can now undergo migration to form a 5 6-membered ring the product. A reaction of this diol to this bicyclic alkene is shown here. In this reaction, once as just we have seen, protonation followed by loss of water can, for example, in this case, generate this carbocation. Once we have this one, as just we have seen, and this can migrate here, so then you will be able to form a 5-membered ring, 4, 5-membered ring with a ketone. Once you form the ketone, you can try to reduce. For example, lithium aluminum hydride, then you will be able to get the corresponding alcohol as the product. Once we have this one, and you can react with acid as just we have seen, and you can lose water, protonation followed by loss of water can give carbocation. Once we form this one, now as we have seen, now this is a 4-member ring. To relieve the strain, it can undergo rearrangement. So you will be able to form a 5-member ring with a carbocation here. Once you form this one, now this can lose proton, then you will be able to get this bicyclic alkene as the product. This slide shows some of the literature examples which depend on the nature of the temperature as well as concentration of the acid that has been employed in the Pinacol rearrangement. For example, here the rearrangement of the diol to this spirocyclic compound shown here, which can depends upon the temperature. You can see here, and in this case, when you have the temperature, lower temperature, this undergoes protonation, then this bond migrates, you get the 7-membered. On the other hand, when you have the higher temperature and this OH group undergoes protonation, then this 5-membered ring expansion takes place and you get this system. And here similarly, when you have the concentration, different concentration also, and you can see here the concentration is when you have the concentrated acid, and here you can see, and this ring expansion of this takes place. On the other hand, when you have higher concentration, the ring expansion of this 5-membered system takes place. On the other hand, when you have the low concentration and the ring expansion of the 7-membered cyclic system takes place, you will be able to get the corresponding cyclic compound. When you have the concentrated acid also, it also undergoes elimination. You can see a double bond is missing. It can also undergo elimination. In this way, you will be able to get a mixture of compounds. So the reaction conditions also very important. As you can see here, the temperature as well as concentration of acid also plays very important role in Pinacol rearrangement. Now let us go for the benzilic acid rearrangement. So here just we have seen the rearrangement of diol to ketone. Here when you have the ketone, diketone doesn't have the alpha hydrogen atom. This is very important. Doesn't have the alpha hydrogen, which can react with the hydroxide ion to give alpha hydroxy carboxylic acid. In this reaction, the formation of stable carboxylate salt is a driving force for the benzilic acid rearrangement. Now let us look at the benzene. When you react with the hydroxide ion, which can undergo addition reaction with carbonyl group, and you get this compound. Once you form this one, now this can rearrange as shown here, and you will be able to get the carboxylic alpha hydroxy carboxylic acid, and after the workup. Here an example shown here. In this case, as you can see here, when hydroxide ion reacts here, then you will be able to form once it undergoes addition reaction, this bond can migrate here, then you will be able to have so if the addition takes place in this carbonyl group, this bond can migrate, you get this carboxylic acid as the product. This what is observed here. The next example involves a reaction of this diketone. This also doesn't have the alpha hydrogen, you can see here. When you react with the hydroxide ion, it can undergo addition reaction with one of the carbonyl group. Suppose if the reaction takes place here, So this can now react here, then this can go here, it can undergo addition reaction, and you will be able to get this carboxylic acid as a product. And similarly here the reaction of this diketone shown can readily react this diketone with potassium hydroxide, and you can get this rearranged product. So far we have seen three types of rearrangement: Wagner-Meerwein rearrangement, where we have seen the migration of alkyl as well as aryl groups. Then we have seen the Pinacol and Pinacolin rearrangement. They have similar kind of reactivity. They are also, if you have the diol, one of the OH group can undergo protonation that can convert in loose water. You will make a carbocation, which can convert into ketone as the product, where we have seen similar kind of, if you have the comparing to alkyl, we have the migration of alkyl group. You can, aryl group also can migrate. Hydrogen also with its bond pair can migrate. So if you see the relative reactivity, the aryl group shows greater reactivity comparing to alkyl. When you have the even electron donating group in the aromatic system, which shows greater reactivity comparing to that having electron withdrawing group. Then we have seen the benzyl to benzilic acid rearrangement in the presence of hydroxide ion. Now let us look at the reaction using diazomethane, the Arndt-Eistert synthesis. And if you have, for example, carboxylic acid, and you can convert into acid chloride, which can be further reacted with this diazomethane in the presence of silver oxide, you will be able to form this carboxylic acid. What you do here, you increase one carbon atom here, and you can also do the reaction with the ketone. Or, for example, if you take this ketone, you can also react with the diazomethane. You can undergo addition reaction. So now this can rearrange, you will be able to form, for example, if you have, if this rearranges, you will be able to get this ketone, where you add one carbon CH2 extra. And similarly, this also sometimes it can also cyclize, and you will be able to form epoxide. Similarly, we have the carboxylic acid. I can convert into acid chloride, which also can be reacted, and you will be able to get carboxylic acid with one carbon more. And here the mechanism shown. Let us take this acid, an example. When you react with thionyl chloride, you will have this salt. Once you have this one, now this can undergo addition reaction. This way you can generate the acid chloride. Once you form this acid chloride, now you can try to react with the diazomethane as just we have seen. So this can undergo addition reaction. You will be able to form Once you form this one, this can lose proton because acidic. You have this proton, you have Cl minus, then it can lose proton, then you will be able to form so this can you can once you form this one, this depends upon the reaction conditions. For example, if you have water nucleophile which can undergo addition reaction, and then you will be able to form the corresponding carboxylic acid. So if you remember here, you add one CH2 extra in this case, and so you will be able to, for example, you start here with the carboxylic acid, and you have this carboxylic acid. You can see the addition of one CH2. This also very important reaction. As you can see here, the diazomethane also can be made, easily made. They also, once you form this one, which can undergo addition reaction with acid chloride, and you can do homologation like this. Now let us look at some literature examples. You look at this carboxylic acid, and when you react with oxyl chloride, you can convert it into the corresponding acid chloride, as just we have seen the reaction with using thionyl chloride. Once if you have this one, this as just we have seen, you can try to react with the diazomethane, and you can convert into the isocyanate. Once you form this one, and which can be further reacted with the nucleophile, you will be able to get this carboxylic acid. Here also the reaction of this acid chloride is shown using diazomethane, and you can also generate the carbene using light, and you will be able to form, which can now undergo rearrangement. Once if you have this one, in this case the reaction of methanol shown, which can undergo addition reaction. For example, when you have this acid chloride, when you react with diazomethane, you will have once we have this one, as just we have seen, and the presence of light, it can convert into carbene, as just we have seen, this can migrate here, and you will be able to form so once you have this one, this can now undergo reaction with methanol, addition reaction. So you will be able to get this ester as the product. In summary, today we have seen 4 types of rearrangement. We have seen the Wagner-Meerwein rearrangement, where you form a carbocation, this carbocation undergoes rearrangement to give the more stable carbocation. In some cases we have seen the more strained ring undergoes rearrangement, you will be able to form carbocation, which can, and depends upon the reaction conditions, it can undergo reaction with the nucleophile or it can lose proton, you will get the product. Then we have seen the Pinacol rearrangement. If we have the diol, and which can be converted into ketone using acid, we have seen some examples. And if you see the reaction, both Wagner-Meerwein as well as Pinacol rearrangement, they are stereospecific. And then we have seen the benzilic acid rearrangement. If you have the diketone, if that diketone doesn't have alpha hydrogen, so when you react with hydroxide ion, it can undergo rearrangement to alpha hydroxy carboxylic acid. And this is, we have seen some examples. Then we have seen the homologation of acid chloride. If you have the acid chloride, you can try to react with the diazomethane. Once you form this one, which can be further reacted with water, in this way you can increase one carbon, one CH2 addition into the carboxylic acid. This is known as Arndt-Eistert synthesis, where if you have the carboxylic acid, you can try to react with the diazomethane. It can increase the homologation of this carboxylic acid. If you look at the reaction Wagner-Meerwein Pinacol rearrangement, where the aromatic group migrates much faster comparing to alkyl group, and this is due to the enantiomeric assistance. We have seen some examples, and with this we conclude this lecture. Thank you very much.